Hello friends, welcome back for another NLP project using FNet. Here we will do the topic modeling. The topic modeling is nothing but detection of the topic based on the content provided. So before building the model, make sure you are having accelerator GPU T4 and environment preference. Always use latest environment in your Kaggle notebook, and I am using a dataset available in the Kaggle platform, that is topic modeling on emails, and I want to show that dataset to you guys. So let's move on to the dataset part. So here this is the dataset, text classification on emails, and this dataset contains these subdirectories. One is crime, the second one is entertainment, third one is politics, and the final one is science. And here I want you all to notice the number of files available in each subdirectories, so that we will compute the class weights, because it is highly required, because this is a unbalanced data set. So you notice we have 1100 files in crime, 1053 files in entertainment, 3001 files in politics, and 4000 files in science. It's an unbalanced data set. Remember this. This is the data set through which we will implement our model. And let's go to the model part. So before building the FNet model, let's discuss on the FNet model in Notepad. Let me open it. Let's close all tabs. Yes, so let me increase the font. Okay, so FNet is a modern attention-free multi-layer perceptron-based model which uses a similar block to the transformer block. However, FNet replaces the self-attention layer in the transformer block with a parameter-free 2D Fourier transformer layer. So let me rise so that you can understand it better. FNet. The FNet is a modern attention free multi-layer perceptron based model which uses a similar block to the transformer block. However, FNet replaces the self attention layer in the transformer block with a parameter free 2D Fourier transformation layer. So it is very simple. You might be thinking, what is a 2D Fourier transformation layer? So basically FNet or Fourier transformer layer is a simple sequential model built with two dense layer and a dropout layer. So let me create the architecture of this. It looks like the first one is a dense layer with some units and GALU activation. Then a dropout layer with some dropout rate. Then the third one is again a dense layer with the same number of units available in the first dense layer. So this is the basic architecture of FNet, a multi-layer perceptron based model which replaces the self-attention layer. So the advantages of this FNet over the transformer blocks or transformer based models are that FNet is 80% faster than BERT, which is a transformer based model on GPUs, and 70% faster on TPUs. And reason for this speed is Fourier transformer that is unparameterized, and the time complexity is big of n log n, but because of self-attention in transformer blocks, the models will have big of n square, but in case of FNet, the time complexity is big of n log n. And the second advantage is that it achieves 92 to 97% of accuracy given or resulted by BERT. So let me write those advantages. FNet is 80% faster than BERT on GPUs and 70% faster on TPUs. Then FNet achieves 92 to 97% of accuracy of BERT. These are two advantages of FNet, and here in this project we will be using Keras hub for many purposes, because the Keras hub provides a lot many utilities which is used particularly in natural language processing projects. So here we will be using word piece tokenizer from Keras hub to tokenize the text, and before defining the tokenizer, we first need to train the data set to the tokenizer. So Keras hub makes it very simple to train word piece on a corpus with compute word piece vocabulary utility. We will also use a token and position embedding layer from Keras hub to surpass an embedding layer which maps every token in the input sequence to a vector and a positional embedding to that vector. Do not be worried about this, I will repeat it again. So let's move to the notebook. So first of all, we will import the required libraries. The libraries like Keras hub, Keras, Tensorflow, NumPy. So Keras hub is for pre-processing the data. Keras and Tensorflow are for building the model, and NumPy is for numerical calculations. Let's run this. So it will start this session, might take some time, and it is taking some time to download the dataset topic modeling on emails. So wait a while. After that to use the GPU as an accelerator during training, we need to connect the GPU accelerator through the strategy. So to build that strategy, we are using mirrored strategy method available in TensorFlow. After that, printing the number of cores available. So we are using GPU T4 times 2, that's why we have 2 here, that is number of cores available in the GPU connected to the notebook. After that, using the text dataset from directory utility function available in Keras, we are generating train dataset and validation dataset from the topic modeling on emails dataset. And the first argument in the method is the directory path. The directory path is available in the input section. Go to this section, then copy the data path and copy file path. So that's what I have copied and pasted over here. The second argument is shuffle equals to true, so that the dataset will be shuffled. Then the third argument is subset equals to both. This is to return both train dataset and validation dataset. Then the validation split equals to 0.2, that means 20% of the data is reserved for validation purpose. Then seed equals to 1337, it's the unique value which will regenerate the same data set whenever the notebook is re-executed or the cell is re-executed. Then we have batch size equals to 64, so that in each batch we will be having 64 examples. So let's generate the train dataset and validation dataset. After that, I am fetching the class names by applying the attribute class names to the train dataset. And here you can see the method found 9156 files belonging to 4 classes and 7325 files reserved for training and remaining for validation. Let's see what are those classes. So here you can see we have 4 classes. One is crime, the second one is entertainment, the third one is politics, and the last one is science. These are 4 classes, and as I already told that the dataset is fully unbalanced, so we need to compute the class weights so that model won't bias towards the class which has maximum number of examples. So to compute the class weights, I have collected the counts of each class, that is science count is 4000, politics count is 3001, entertainment count is 1053, and crime count is 1100. Already I have shown this at the beginning of the project. Then I have added all the counts and saved that in the variable total counts. Then as we know, the crime is the first one, that means it is the 0th integer value. So for that we will be dividing total counts upon crime counts. Then for entertainment, that is 1 in the integer format, we will be dividing total counts divided by entertainment count. Then for politics it is 2, therefore total counts by politics count. And then for science it is 3, therefore total counts by science count. And we are rounding up to 2 decimal places through numpy's round method. And here you might be thinking how this 0, 1, 2, 3 I have taken. You can see in the class names we have the index of crime equal to 0, the index of entertainment equals to 1, the index of politics equal to 2, and the index of science equal to 3. That is the order in which the model learns. That's why we also having the same keys in the class weights. So let's run this and generate the class weights. Class weights are computed successfully. Let's see that. So you can see the crime count has 8.32 and the entertainment count has 8.69, the politics has 3.05, and the science has 2.29. As the science has maximum number of examples, that's why it has lower or smaller class weight, while the entertainment has the higher class weight because it has less number of examples. After this, I have converted all the strings or text available in train dataset and validation dataset to lowercase. For that, I have implemented a map method inside which I have specified a lambda function which takes two parameters x, y, and for x it will convert the case and for y it won't do anything. Then it will return both lowercase x and y as a tuple. So let's run this and convert all text to lowercase. Yes, it is done. After that, let's see one text and label from a batch available in train dataset. So you can see this is a text and its label is this 3 for science. After that, we are moving for text tokenization. So before text tokenization, I am decoding all the text to the format UTF-8 so that we may not get Unicode decode error, and then I am taking out dataset from the train dataset to train our word piece tokenizer. So we have to take out only the X, that is text, and we should not take out the labels. So we will have all texts in the word piece dataset, and to train the word piece tokenizer we have a method called compute word piece vocabulary, which will compute the vocabulary and returns the vocabulary. So with that method we are computing the vocabulary for the tokenizer. So here we are providing first training dataset with all text only, then vocabulary size is 15,000. This is the max vocab size, and we have reserved tokens pad and UNK. So every vocabulary has a special reserved token. One is for padding, another is for unknown tokens. That's why for padding we are using this, and for unknown tokens we are using this. So let's generate the vocabulary and save that in the variable vocab. So word piece is not defined, that means we have to run this. Now we can run it. So it will take some time, and after that we are printing the vocab elements in the index 100 to 115. So generating vocabulary takes some time. Keras Hub is such a nice library which will be used for natural language processing. So see how I am using Keras Hub and learn from this video. Compute word piece vocabulary is available in the tokenizers module of Keras Hub, and we will also use token and position embedding layers available in the layers module of Keras Hub in the future. So it is taking more time, and do not be worried, this will help you a lot when you build large scale projects and real-time projects, and this is also a real-time project. If you change the dataset it becomes real-time project, and you need to carefully handle the hyperparameters. And don't worry, I will teach you and learn with me. Yes, the vocabs are computed successfully. Let's see the vocabs present between 100 and 115. So these are the vocabs: what, would, we, will, and, there, one, all, about, rights, do, know, why, my, has, people. After that we will configure the word piece tokenizer with the vocabulary generated just now. Then we are passing the argument lowercase equal to false. All the text are converted to lowercase. Then the sequence length equals to 512 is given, so that all the sequences returned by the word piece tokenizer will have a length of 512. Let's run this. Up to this we have built the tokenizer. Now we will pre-process using that tokenizer, and to train the model we should have a format of input data to feed the model. So for that we will have a format like this, in which we will have a dictionary and a label inside a tuple, and the dictionary will have a key called input IDs, and tokenized sentence is the value for that key. This is the format in which all the input data we will give or feed to the model. Then we are building a TensorFlow dataset and mapping all the trained dataset and validation dataset to this format with number of parallel calls equals to tf.data.autotune, so that TensorFlow will be allowed to decide how many parallel threads to use when applying the map, and it will also improve CPU utilization. Then we are returning the shuffled dataset and prefetched with 16. The prefetch is done to preload the next batch in the background while the model is training. It will reduce the data loading bottlenecks. Then we are caching the data so that the data will be available in RAM, which can be fetched very quickly, and we are applying this method to both train DS and validation DS. So let's do that and format our train DS and validation DS. So it's done. After this we will build our FNet model, and in our FNet model we will provide shape of data which is unknown and d type of int64, because tokenizer converted that to vectors of integers, and we have given a name input IDs to this input layer. Then, as I already told, we need to do two things. First, a layer which maps every token in the input sequence to a vector, then a layer which encodes word order in the sequence using another embedding layer. So to carry out both these works, or to perform both these tasks, we have a layer in Keras that is token and position embedding layer, which will do all the works does by the embedding layer and position embedding layer. So here we are providing vocabulary size 15,000 and sequence length 512, embedding dimension 128, and mask 0 equal to true. So these arguments are specified. After that we have the FNet encoder layer from the Keras layers. These layers are repeated 3 times so that features will be fetched nicely, and the FNet encoder layer follows the FNet architecture, that is dense layer, dropout layer and dense layer, which is done 3 times with the intermediate dimension equals to 512. Then we have a global average pooling one-dimensional layer, then a dropout layer, and finally we have a top layer for classification, that is a dense layer, where we have provided length of class names as number of units and a submax activation function. Then we are building FNet classifier with functional model architecture. So let's run this and build our FNet classifier. So FNet classifier is built. We will compile the model under this strategy built for using the accelerator. So model will be compiled under the scope of strategy with the optimizer Adam, sparse categorical cross entropy loss, and matrix equals to accuracy. So let's run this. So the model is compiled successfully. Let's train the model with the trained dataset and validate the model with validation dataset, and we are going with 30 epochs, and we have a callback checkpoint will save the checkpoints of the FNet model in the file path called fnet.keras, and this checkpoint or model checkpoint will monitor the validation accuracy and saves the best models in the file fnet.keras. Applied the class weights because the data is unbalanced. So let's train the model. After 30 epoch, we can see that the training accuracy is 0.76 and loss is 2.36, and validation accuracy is 0.64 and validation loss is 0.71. So as the model is not improving, you can apply the early stopping callback, and the maximum validation accuracy reached is 0.72, that is 72%, and maximum training accuracy reached is 89%. So after that, let's load the best model from the checkpoints and evaluate that with the validation dataset. So the best model has accuracy of 0.72 and loss of 0.58. Let's build the inference model, and to build the inference model, we are defining a method get inference model, and under this method we have an input layer which will take string inputs, and then we have a tokenizer which will tokenize these inputs, and we are providing the tokenized data to the best model, and then we are building a functional model and returning back. Then under the strategy, we are compiling the inference model with the same arguments specified during this model, and let's run this. So we have successfully created the inference model. Now let's do the prediction with the inference model. So I have taken a text from Google. This is politics of India works within the framework of the country's constitution. India is a parliamentary, secular, democratic republic in which the President of India is the head of state and first citizen of India, and the Prime Minister of India is the head of government. So let's do the prediction to this. What the model should return? It should return politics, and we have 4 classes: crime, entertainment, politics, and science. Let's see. So yes, our model predicted correctly, it returning politics. Let's change the text. Let's set that. Let's change the text. Let's copy some text from Google. So science topic, let's go with that. Science about human body. Okay, let's take that. Let's copy this up to here. What is happening? We have copied it. Let's paste that. Let's predict. So it is written in science now. After that, set the model with the save method and pass a file path to save. I have passed model.keras, and let's run this to set the model. Yes, model is saved successfully, and you can download the saved model in the output section. Click on this triangle symbol, so it will load. Wait. So here FNet.keras, click on the three dots and click on the download button to download the checkpoints file. Then to download the model.keras, click on the three buttons, then click on the button. This is the way to download the model. So thank you very much for listening me patiently. Have a great future and a good life. Take care of all your family members. Thank you very much.